In this lesson, we're going to take a look at how to solve a kinematics problem. Now, we have our kinematic equations. Change in position equals 1/2 at squared plus v naught t. And remember, we can write that as x equals 1/2 at squared plus v naught t plus x naught. We have final velocity equals initial velocity plus acceleration times time, which is really just the definition of acceleration, right? Change in velocity divided by time equals acceleration. And then we have the combination of these two things, final velocity squared equals initial velocity squared plus twice the acceleration times the displacement. Now, these equations are valid with constant acceleration. If we don't have constant acceleration, then these go out the window. But we're primarily only going to see problems with either no acceleration or constant acceleration, so it shouldn't be too much of a problem. Now, all we want to look at here is how to use these equations to solve problems. So let's say that I have a car, and it's traveling with an initial velocity of 25 meters per second. And it applies the brakes, and it comes to a stop in how far if it accelerates at, say, 10 meters per second. Now, the first step that I always want to do when I'm solving problems is write down what I know. What I know are my given information. And so what I'm given is an initial velocity, v naught equals 25 meters per second. If it comes to a stop, that tells me a final velocity, v equals 0 meters per second. How far is what I want to know, and it accelerates at 10 meters per second, per second. So that acceleration is actually negative because what I've done is I've assumed that the car is moving this way with a positive velocity of 25 meters per second. And a little bit while later, it's going to have stopped. It won't be moving at all, and so it's accelerating against that velocity. And so if my initial velocity was positive, my acceleration is negative 10 meters per second per second. And what we want to know is how far, that is its change in position or displacement. So there's a couple equations that I can use that involve displacement because the second equation has a displacement in it and the first equation has a displacement in it. If I look at the first equation, I can find displacement if I know acceleration, time, and initial velocity. Well, I know acceleration and initial velocity, but I don't know time. Second equation, if I know an initial velocity and a final velocity and an acceleration, I can get a displacement. I just have to do some algebra and rearrange it. So that's the equation I want to use. It's got the information that I want and can get me the information that I need. So I'm going to write that equation. What formula am I using? So the formula I have is final velocity squared equals initial velocity squared plus twice the acceleration times the displacement. And now I can either put in the values or I can solve for displacement. I'm going to go ahead and solve for displacement. So that means I want to isolate that variable. So I'm going to subtract v naught squared from both sides and get v squared minus v naught squared equals twice the acceleration times the displacement. And now I can divide by 2a, divide by 2a, and I get a displacement is equal to final velocity squared minus initial velocity squared divided by twice the acceleration. And now I'm going to go ahead and put in my values. So v squared is 0 minus 25 squared over 2 times negative 10. Now, don't let the negatives mess with you. This negative is not included in that square, and so what I get is negative 1225 divided by negative 20. And I can see that my negatives cancel out, which is good because this thing was initially moving with a positive velocity, so it should have a positive displacement since it's coming to a stop, not reversing directions. And then I get 61.25 for my displacement, and that is in meters. Now, I did not carry my units through. That's generally speaking a bad idea, although you can get there. So let's double check our units. So this is 25 meters per second, but we squared it. So I have meters squared per second squared divided by twice an acceleration. Well, an acceleration is a meter per second squared. When I divide fractions, remember that's invert and multiply, so I have meters squared per second squared times seconds squared per meter. My seconds squared cancels my seconds squared. One of those is gone, and so I am left with meters. So dimensionally it checks out as well, 61.25 meters. So we can figure out how far this thing went as it stopped. It went just over 61 meters. Now if I want to know how long it took, I just have to pick another equation. And now I could use either of them, right? I could use my first equation because I know my delta x, and I know my initial velocity, and I know my acceleration, so I could find time. Might be a silly way to do things because that time involves a quadratic equation, and I don't want to solve the quadratic if I don't have to. So I'm going to use the second equation, v equals v naught plus at, or final velocity equals initial velocity plus acceleration times time. So 0 equals 25 plus negative 10 times t. Now I'm going to subtract over that 25 and get negative 25 equals negative 10t, and then when I divide both sides by negative 10, I do see that time is in fact a positive 2.5 seconds. If I had gotten a negative time, I know I had messed something up.